Imagine waking up in a completely featureless void, with no landmarks, no horizon, and no stars. In this space, there is zero mathematical difference between falling at 1,000,000 miles an hour and standing completely still. To track reality mathematically, we cannot rely on empty space. We have to construct an anchor. We need a single, arbitrary 0 point to ground the universe. We call this origin point O and place an observer at this coordinate. Motion requires time, so they are equipped with a clock. From this observer, we construct a 3D mathematical scaffolding that radiates outward, mapping every possible location in space. This handwritten note highlights the exact definition. This entire system, the coordinate axes attached to an observer, specifically having a clock with him to record time, is called a frame of reference. Without this structure, the concept of movement is meaningless. Absolute motion does not exist. Any scientific claim about an object's speed or trajectory is only valid when tied explicitly to a constructed frame of reference. We can test this framework on a real-world scenario by measuring the speed of passengers inside a moving vehicle. We have observer C standing still on the side of a road while a car drives past carrying passenger A in the front and passenger B in the back. If we use observer C as our frame of reference, the math is simple. The car and everyone inside it is moving through space along the x-axis. Watch what happens if we shift the mathematical origin point to the passenger in the back seat. Now the car is perfectly still, while the road and observer C slide rapidly backward. Look at passenger A in the front seat. Relative to our new origin point at passenger B, their spatial distance never changes. This text note summarizes the result of our shifting framework. With respect to C, passenger A is in motion. But directly below it, with respect to B, passenger A is at rest. Both statements are simultaneously true. Rest and motion are not absolute properties of an object. They are flexible relationships dictated entirely by where we choose to place our 0 point. To understand how we measure this movement, we need to strip away the complexity of the 3D world and look at a single straight line. The first metric we use is distance. This is the raw accumulation of the actual path an object travels. Distance only records magnitude. It doesn't track which direction you face. It simply grows continuously as you move, acting as a strict scalar quantity. Because distance is a historical record of ground covered, we see in these handwritten rules that it is a scalar quantity and can never be negative. You cannot untravel a path. Physics requires a second metric, displacement. Unlike distance, displacement completely ignores the meandering path you took. It strictly looks at the net change. It is the shortest geometric vector pointing straight from your initial starting coordinate to your final ending coordinate. We write this state change algebraically, as seen in this boxed formula. Delta x equals x2 minus x1. Final position minus initial position. Classical mechanics tracks both because they answer different questions. Distance tracks the exhaustion of resources, like the fuel burned in an engine. Displacement strictly tracks the net geographic result of the journey. Because distance tracks the full path and displacement tracks the shortest path, they are bound by a strict geometric relationship. There is only one condition where the magnitude of displacement perfectly equals the distance traveled: when an object moves strictly in one direction along a straight line. If that particle stops and reverses direction, our distance counter just keeps climbing higher. It's still covering ground. Meanwhile, because the particle is moving back towards its starting origin, the net change in its position is shrinking, driving displacement down. This divergence establishes the primary axiom of motion shown here. Distance is strictly greater than or equal to the absolute value of displacement. The exact moment an object changes direction, it permanently breaks the symmetry between its scalar history and its vector state. Distance will always outpace displacement from that point forward. This brings us to a common mathematical confusion. If distance is always positive, why do vector states like displacement constantly use negative signs? Look at a purely positive displacement. Moving from 0 to 3 yields a positive 3 meters. The plus sign simply means we moved in the primary, forward direction of the axis. Now watch what happens if we move from 0 to negative 3. The result is negative 3 meters. In vectors, a negative sign doesn't mean less than 0. It is a strict geographic instruction pointing in the opposite direction. This creates a fascinating mathematical edge case. If an object travels forward, then loops back to end exactly at its starting coordinate, its initial and final states are identical. This chart shows the exact calculation of that loop. The object covered a total distance of 6 meters, but as highlighted above it, the mathematical displacement is precisely 0. In kinematics, a negative sign is a precise compass heading, mapping the exact direction of travel against the arbitrary frame of reference we built. Pulling back to three-dimensional reality, as a particle traces a chaotic path through space, its distance acts as a constantly accumulating scalar footprint. Simultaneously, the displacement vector tracks the shortest net difference from the origin, ignoring the path's meandering history to calculate current state. But neither of these precise measurements means anything without the specific observer anchored at point O. Establishing these two distinct metrics, the scalar history of distance and the vector state of displacement, is the mandatory first step before physics can calculate velocity, acceleration, or force. By defining our frame of reference and separating distance from displacement, we translate the observation of movement into precise coordinate data required for advanced physics.